So hello everybody, I'm Quentin from the team Ecole Polytechnique, and I'm going to present problem number 1, the sound thermometer. So the problem states that we need to devise a method to obtain the temperature of a fluid by pouring it into a cup. And it wants us to state the precision, the accuracy, the limits of our method, as well as the important parameters of the fluid. So just a disclaimer, I'm not going to use any other fluid than water because I'm not going to heat some ethanol or glycerol. So my fluid is going to be water. So first, I'm going to present two sounds and see if you can intuitively guess the temperature of the two sounds. So here's one. And here's the other one. Well, I think you get it, that the left one is cold water because it's more harsh, and the right one is the hot water. So the question now is, why are these two sounds different? So first, a very short preliminary analysis of the problem. So there is viscosity, surface tension, and density that are important in our fluid. And the most important is the viscosity because it varies from 0.18 to 0.04, which is one order of magnitude, whereas the two others stay at the same order of magnitude. So here's our experimental setup with a water tank and a water container to give a constant speed, a high-speed camera, and a microphone. And here is one experiment we did with this setup. Okay, so here is the temporal fluid transform of this experiment. You see that it's quite complicated. We have kind of three zones. The first zone over here, a big zone with a lot of sound, and an end zone over here. So let's compartment the Fourier transform. The middle zone that we'll look after, and the first zone over here, the zone on the side with the transition from the first to the middle and to the end. And let's look at this one. So first, let's look at liquid jets. Liquid jets, they have an instability with a wave that can propagate and be amplified on the surface of the jet, and that's called the Rayleigh plateau instability in the literature. And it has a characteristic length that is 2 pi the radius of the jet. And this leads, by correlating it to the speed of the jet, with a frequency when it's hitting the bottom of the water, that is about 210 hertz. Experimentally, it's more complicated because you have small and big drops, and we get a frequency that is between 100 and 300 hertz, meaning that we can explain the two first zones of the two first amplitudes of our spectrum. This is superposition of a few Fourier transforms from our experiments. So we get this part of the Fourier transform. Now let's look at the three different interactions that we have. We have a first interaction, which is a drop water interaction, drop surface interaction. Sorry, it's colliding on the surface. Then you have the drops. Still, the drops are colliding on the water. It creates bubble over here, and then you have some jet when it's not anymore the drops that are hitting, but the jet that is colliding with the drops and creating some new things. So these are the three parts, and they explain why we have this first. The middle, that is the drops hitting on the water, and this part is the jet interacting with the water. Now, let's look at what happens with the frequency of the sound. What makes the sound? It's actually known in the literature. It's the Minière frequency that is proportional to 1 over r. And we tried to verify this frequency. We got an experimental setup when we have an injection of air into the water. We record it with a microphone and we film it with the camera. And we get an experimental, a good correlation between the theory of Minière and our results. Now that we've understood the lowest part, that's the creation of the bubbles when the drops start to interact with the water, we have to look at what happens over here because there seems to be two zones. And that's because you have a cavity. The cavity, by cavity, I mean the air cavity inside the box we use. We did two experiments. One experiment where the bubbles can flow outside of the whole water tank, and one where there is a cavity that maybe something can happen into it. And you see that you have two very different Fourier transforms. Let's try and understand this. Is there an influence of the water? So if we put more or less volume of water, we see that we don't have any difference. But now if I use an influence of air, we see that if I use two cavities that are of a different length, you have for the lower length, you have the frequency that goes up. So this can be so there is an influence of air, and this can be explained by the resonating cavity model. So you get that the frequencies amplified are the odd values of C over 4L, and the attenuated frequencies are the even values. Now let's compare with our experiment. Before the first frequency, there is no amplification and no attenuation because the wavelength is too big for the cavity. Then you have the amplification of two frequencies here, the first and the second, and if you compare with our theory, it predicts that you have the difference of the two is a factor of 3, and that's what we get in our experiments. So this is the way we get the method, the best method we got for finding experiment, because we can get others, but we used to get the constant height. We used this model, this experiment with a tube that has the water going out the other way, and from this we know that the temperature of sound, the speed of sound in the air varies with the temperature. Between 0 and 100 degrees Celsius, it varies linearly in the function that I put over here. And so we can get from the frequency that is resonating into the cavity by putting a microphone up there, we can get a prediction of the temperature of the fluid, which is the temperature. And from our experiments, we can say that the precision is about 5 degrees Celsius. Now, we've understood this part of the Fourier transform. And there are two other parts that can maybe lead us to new ways to find the temperature. So the first part, we see that the frequency is increasing as the water goes into the water tank. So that's because when we pour water into it, there is an evolving resonating cavity. And so if you put alpha, the diminishing weight of the cavity, you see that we can fit the sound characteristics with this function, and it really correlates with what we want. So this part, this increasing part, is due to the resonating cavity, the time, and the linearity of the filling of the water tank. Now there is another part over here, which is low frequencies being created, and that's understood in the literature when you have coalescence of two bubbles. So there is a sound frequency. The literature says that the sound frequency was the Minnaert frequency of the large bubble, and so the expression of the total frequency of the new bubble can be expressed as the function of f1 and f2, the two frequencies of the bubbles. And we tried to find if this fits with our theory. So here we plot the Fourier transform in blue of one of our models, and then I used a normal distribution of bubbles around the main frequency. And I tried to each time to coalesce them mathematically, and I get a good prediction of the other amplitudes that appear in the Fourier transform. So that really correlates with what we want with the coalescence. So we've explained the up, the down. So we've explained the whole Fourier transform. To recap, the method we use, and there are other methods which I will be very happy to discuss, but the best method we can find is to find the temperature using the special setup of a flow that is going outwards of our setup. We get the temperature that is the temperature of the fluid with an approximation of about 5 degrees, and certainty of about 5 degrees. And to emphasize the fact that we need a special setup, I did it in a cup, so regular mug. And the fact that you don't have any ejection, so the cavity changes over time. The fact that the cavity changes over time, you don't really know when to take the frequency. And so if I try to do it with this cup, I don't get any prediction like I would in the special setup I used. So to conclude, the phenomenon we are looking at here is the phenomenon of a water container pouring water into the water tank. There are three main parts in the Fourier transform. A first part where you don't see any amplitudes because there are amplitudes, but it's shock amplitudes, so they're very low compared to the creation of sound created by the bubbles into the water in the second part. And the first part actually is the jet that is just interacting with the bubbles that are coming up once again. And that's a really shallow sound compared to this one, which is rather big. Then we explained the influence of the cavity for the going up and the selection of a few frequencies, and also the going down with the coalescence. And we get a predictive method that is giving us the temperature of the fluid with a prediction of about, with an incertitude of about 5 degrees. Thank you.
Okay, in the meantime, I shall start without the slides. Okay, so first of all, okay, that was a really impressive presentation. I mean, you covered everything greatly, the theory and the experiment. The experimental setup was amazing. What I didn't see, or okay, let me continue with the pros some more. So you did the complete theoretical analysis, and you had all the possible sounds made by water on a container, the bubbling sound, the drops falling at the base of the container, and the jets going directly into the water, and you greatly analyzed how these affect the spectrum. And indeed, in the experimental results, you showed us that the spectrum was what exactly we expected. But the thing is that, we saw that for the container which never fills up, so that means that there is no resonating, there is no changing resonance of the cavity, which, you said, further complicates things, but I think it is possible to actually isolate these frequencies and remove them. And you also were a bit too quick. I mean, I missed you at some points, especially in those parts where you talked about the exact formulas, but okay, I guess it could be just me. Another problem I had was the container detached from the workstation? I mean, when you have a container like the one with the constant cavity on a workstation, now the workstation echoes differently and amplifies certain frequencies. And when you record this should be in your spectrum. Now, I don't know how was that, but I guess you will explain to us later. Okay, anyway, some further discussion. I have the further discussion at the end too. I have another 3 minutes for that, right?
Yeah, sure.
Okay, so I'm going to dwell on the cons a little more. Okay, the one, for me, the greatest con is not to be able to predict the temperature of a cup, because the problem, I did that problem too, and I could not really predict the temperature of the cup, but the problem clearly states that the temperature should be from pouring liquid on a cup. So that means that, yes, I guess if your cup was big enough to have a constant cavity, yeah, you could say that you solved the problem. Okay, that was it from the cons and the pros. Now, for further discussion, and I may move in the next part, I would like to see a new way to actually isolate these resonating frequencies of the cup, the cavity that forms, and how we can get rid of it. I mean, it's pretty complicated, and I don't know how you could do this, but I guess you guys did all that you could. And we could try other liquids too, see how viscosity affects the problem, surface tension. You showed us that I think this was for water, exactly, that the surface tension and viscosity changes with temperature. And we could also do it from other heights, because the velocity of the pouring water changes the higher you get, of course, until a certain height when there is a U-crit, when you can't go any higher than that. Okay, and finally, I would like to see a general equation like, okay, these are the frequencies. This frequency has an intensity of, say, 50 decibels, and that tells us that's exactly its temperature. I mean, an equation that from the one part of the equation is the temperature, and the other part is some function of the frequencies and the intensities. And last but not least, to automate all the sequence, like have a device. I mean, that would be really cool. Have a device that actually I can just put it next to my cup, pour down my coffee, enter the viscosity, and tell me what's the temperature of my coffee, so I don't burn my tongue. Okay.
That's time for discussion.
Okay, so I really like you talked about other things, because in our setup is quite difficult, and actually we did other methods, and I talked a bit about impression. So if I mean do it, I'm going to show them to you. And I use the things I talked about, because as you said, there's a lot of physics here, and it's quite hard to present everything. Okay, so that was my conclusion. And then, Yep. Okay, so yes, that's it. So I talked about 3 different parts. Remember the dropping part, the middle, and the last.
Yes.
There's the first method with the drop impact because the viscosity varies. So if you have more force, if you have a low viscosity, you're going to eject more liquid outside, so you're going to transmit less force to the surface. And so being the hot water being of a lower viscosity is going to have less force than the hot water. And so for this, we measured the square root of the whole amplitude of our signal for drops hitting the bottom. And over the temperature, we get some correlation, but we don't get some precise thing because it's kind of really hard to get the same experiment every time.
Yeah.
And so this is only a comparative method. I titled it the comparative method because, like with the ear, you know, at the beginning, you can really say, okay, this one is hot, this one is cold, but you can't say the temperature of the cold one. You can say it's 20. And so for this one, if you compare 2 liquids based on the statistics we have over all our points, we have a probability of comparing 2 fluids by 90%, saying, okay, I predict this one looking this method, and I get the right temperature.
Yeah.
That's one method. I have 2 others if you want, so the water interactions. There's the first one over here. So that's another thing. But this one. So that's the jet-water interaction. So you have the jet that is destabilizing over time. And so you have the transition from a normal jet to the bubbles. And so you have these frequencies which are going to be really shallow. You know the transition I showed at the end of the Fourier transform. And so for this, sorry, I have quite a lot of stuff. And so okay. So for this method, actually you can find the speed of destabilizing of the jet. It's really a simple formula. It's the square root of rho a squared, a being the radius of the jet. That's the time. That's the time of the destabilization, and you get over gamma, which is the surface tension. But actually, what you don't take into account is the viscosity, and the viscosity is going to change this formula, and so you're going to have with a lowest viscosity.
But
yes. Okay.
how is this related to the frequency? I mean, that's just the time it takes to deform.
Yes.
Right.
And so it's going to be correlated to the time of transition from the bubbles to the normal jet.
Oh.
And this time is going to be correlated with the temperature. And so from this we get also not a good fit for the perfect temperature, but you get also another comparative method, which is a bit worse than the previous one. You get about 60%.
The thing is that when you hear it with your own ear, as you said, you can clearly hear the difference.
Yes.
And the thing is, if the human ear can hear it, then the information that one liquid is hotter than the other is there. So it's just a question if we can decompose this problem and say, okay, here's the important parameters, and I can really study them and give you a pretty equation which gives you directly the temperature. But the thing is, why is it so hard to actually do this? Because you said that these are the 3 ways that water interacts with itself and produces frequencies, different frequencies. But indeed, we can't really. This is worse than from the human ear. I mean, this doesn't predict temperature better than the human ear.
Well, I don't know if you tested for everything, but if you try to trick the human ear, it's actually quite possible. The best way I found that you can really predict the difference between 2 liquids, so it's once again the comparative method, is the one I talked to you before about the hitting on the surface. And if you remember the 2 sounds I showed you at the beginning of my presentation, the hot and the cold, you really hear at the beginning when it's hitting the bottom of the cup, you really hear it's really not the same sound. The cold is really more harsh and more powerful than the hot.
Yeah,
and that's the best method. That's what I think the human ear does.
Okay, yes.
All right. So my name is Ivan Žugac. I'm from Croatian team, and I will be reviewing the problem as sound thermometer. So I will first review the reporter. So there were many good points. One of which is that it is through roughly studied, well presented, and there was a really good theory background. So bad points. You mentioned the parameters briefly on the beginning of presentation, but didn't mention them until the opponent asked you. So throughout whole presentation, they didn't seem to matter. You didn't. One of the questions of the problem was the accuracy. I didn't hear you mention any of that. You mentioned precision, but not accuracy. Also, you didn't state. You didn't state. I didn't. For me, it was unclear exact correlation between what is the most significant part that correlates with temperature. Now, for the opponent, he mentioned some problems with the cup regarding frequency change and change of a variety of initial conditions in your experimental methodology. Now, the bad points, he also didn't recognize that you didn't talk parameters, which is for me very important for the whole model and the whole method. Now, what I would like you to further discuss, how exactly parameters fit your model in terms of frequencies, how geometry of glass maybe plays part, how different gases affect the result, and what is the most significant source of sound. What you would say is the most significant source of sound. Thank you.
Let's move on to discussion.
Okay, so maybe I'll just start with the parameters of the fluid because I think that they're really important, and the most important one is the viscosity. In the cup, when you have the cup, it's hitting the bottom, and the viscosity is going to change the force transmitted to the cup. That's for the comparative method we use. But for the predictive method with the tube, we don't care about the viscosity or the other parameters because we only care about the temperature with the capacity of the air in the tube being able to heat the air around and to create a sound wave. But the sound wave is in the air, so the water doesn't change anything.
I think that the most important parameter is not the viscosity, but the surface tension, which changes accordingly to temperature. And this is what holds the bubble together and changes its radius. So the surface tension goes like T, which means that it decreases linearly with temperature. That means that the radius of a bubble, which is a major part of the sound we hear, it's not when you pour water, you don't hear. You hear in the beginning that first part of the three sounds, but you hear also the oscillation of bubbles. Now the bubbles, you said from the mean average formula, are their frequencies are f.
1 over r.
1 over r, right. So the radius changes with to the power of 1
1 over r.
over 3, no. And the frequency changes accordingly. So we could see how temperature affects the bubble formation inside the container and see which of these frequencies we hear, and by looking at the container and hearing its sound, we can tell the temperature.
Okay, so
that's really important.
Just to for
Okay,
this.
can I just
Okay, yeah.
so parameters of the fluid that affect result, your opinions obviously depend on what is the most significant source of sound. So can you tell me please firstly, what do you think is the most significant source of the sound in this problem?
Yeah, it's as I showed in the Fourier transform, in the big part in the middle, and that's the oscillating bubbles. So
Oscillating
right.
bubbles.
yes, exactly.
You?
Yeah, I agree.
You both agree.
Mhm.
So do you think that the surface tension plays part, for example, bigger bubbles, for bigger bubbles or smaller bubbles, does surface tension plays a role?
It doesn't. Well, I want to show you something. It's the fact that I recorded without the cavity. So the first, when I started to talk about the cavity, remember I talked about the cavity being filled and the other one being completely open. And the one filled, if we go back to the Fourier transform I got for this experiment, actually you see that you have all the frequencies going up to 10,000. And that means that the drop of the bubbles on the water is so chaotic that you have all the frequencies that are created with many sizes of bubbles. And if I go back to the video I wanted to show you, I showed you at the beginning, so these ones, you see that there are the really, really big, small bubbles here, the medium bubbles, the big bubbles, the recombination, the coalescence. It's so messy that I didn't see anything with the
It's
surface
messy,
tension.
but if you look at it at different temperatures, you can see different distributions of different radii. So, for example, for higher temperature, you could have many bigger bubbles because it goes inversely, right? So with higher temperatures, you have bigger bubbles, so lower frequencies. So from this you can tell the temperature.
Well, it's
and looking at it and hearing sound. I mean, it's not exactly a sound thermometer, but
I agree, and that's the part of the coalescence. That's the coalescing part because you have the first part going up with all the small bubble, the medium bubble is created at 1,000 Hz approximately. And you have the coalescence going down. And that's really interesting because it's studied in the literature, and it says that with temperature, the coalescence increases. And that's the third method I wanted to present you that that I got for the prediction of the sound. And it's used for the frequency.
Okay,
Yeah.
I would just like, before the teams, I would just like to ask, how do you think that the frequency would change if we would to introduce another gas, of different gas, for example?
Different guest or
Yeah,
guess?
if we wouldn't have air, but some different gas.
Okay, I can answer that really quick. I mean, we said that the most important parameter is the oscillating bubbles. Now, a bubble will have a radius which will be proportional to the. Now, this is an empirical equation, but okay, it depends on these parameters. There are some things here that, like surface tension and other things, but this is the difference of the densities. Now, for another gas which has a different density from water, this thing would increase, decrease, I don't know, but it would affect the radius of the bubbles like that.
Okay.
So, because the temperature goes like the frequency goes like 1 over R, you can tell that this would affect the frequency of the bubbles. So, you can tell that.
Okay, great.
If I may answer to this, I think I showed with the frequency of the container that it's too messy to have only one frequency created by one radius. So you can't really do this, but maybe if we look at our method with the special setup, so if I clean this, actually the speed of sound is gonna change with a square root of the, so the speed of sound is gonna be some square root of RT over M, M being the volumic mass of the gas. And so if you change the gas, you change M, and so you change the speed. And maybe if you disperse, like you have a higher speed, you disperse more of the values, you can have maybe a better correlation, but it's not going to improve like 5 degrees.
Great. And what do you guys think about the geometry of gas? How that change the frequency here?
Gas of the glass.
Glass, sorry.
Oh, yeah. So obviously for the cavity, it's going to change a lot. In the cup, it's quite hard to find it, even in the shallow cup. If you could do a bigger cup, you can have a quite good approximation, maybe 20 degrees. That's the best thing we can
The bigger
get.
the cup, the lower the rate of which its resonating frequency changes, because the height of the liquid changes really slow. So you can isolate that resonating frequency and get it out.
Did you actually guys try different cups?
Yes,
Yes.
Yes. And what was the results?
Okay, so for the different cups, well, for the small one, so just a mug where you drink your coffee, it's not possible. If you do a more precise cup, you get an approximation of about 20 degrees, but it's not really good. And for the special setup, you get the 5 degrees I talked about. So.
Okay.
May I ask, you present us this beautiful Fourier transform diagram. I just wanted to ask, is this something that you see constantly, or is it a diagram that you got once?
That's the problem when you do some presentations like this. No, we get, if we control the experiment, we have the same look, but what's going to change is the transition from Rayleigh plateau, which are these frequencies, and are going to happen here. So this one is going to be quicker. For the hot water, you're going to have more coalescence, so you're going to have a bigger impact here. And for the hot water at the beginning, you're going to have more frequencies over here.
So you have the same angle over that line that you present all the time?
That's going to change with the cup, because that's due to the filling rate of the cup, which is
No, in the same setup. You always see the same.
yes, exactly, always the same.
The same Fourier transform?
Yes.
Okay, thank you. Please.
How do you prove it's the bubbles we hear and not the splashing on the surface? How would you prove that's what?
Okay, yeah, exactly. So I can prove this by another experiment. I just look at one bubble that hit the water tank. So, and actually you see that if you don't have the creation of bubble, you don't have the okay, yes, there you go. So that's one experiment with one bubble. That's a bubble hitting the drop. And so you're going to see it's going to splash once again, separate into smaller drops. And then when it comes back, it's going to create a little bubble under the surface, right here, this one. And now if you look at two experiments, so one with no bubble being created, and one with a bubble, so that's the same experiment, we don't care, but this one is the one with a single bubble. And so you don't have anything.
Can you play the sound, please?
Huh?
Play the sound, please.
Oh no, the sound is not going to work because there's no sound. Okay, maybe I can play it to you, but it doesn't. There's no sound because it doesn't make any sound. And if you want to look at at the actual spectrum, it's this one. So you get the impact of the drop. You can correlate the two impacts of the drop with the same shape over here. And you see that the positive one, so the one that makes sound, is going to be more powerful. So it's going to go upper here. And then when you have the creation of the bubble, you can correlate it with this frequency, which is, for this experiment, about 2,000 hertz, because it's a very small bubble. And that's when the bubble and the sound that you hear is tick, tick, tick happens.
Thank you.
Thank you. Oh, time is up.
Okay.
So we have 1 minute to make conclusions.
Okay, so I think we really well understand the problem. The problem is really complicated. There are many phenomena. I talked about the 3 different parts, and I have a very good method to define the temperature. For the accuracy, it predicts the temperature within the range with an accuracy of about 5 degrees. Then there are 3 other methods that we discussed. We discussed the impact of the fluid. Maybe it would be interesting to look at what happens with the. We tried, but we didn't push it that far with the importance of the cup being filled, because I talked about the frequency going up, and maybe if we fill the cup, but it's going to depend on the size of the cup. So it's quite a complicated thing. The creation of the bubbles is really messy, but I think we got a quite good understanding of what happens here. Thank you.
Thank you. Now we have time for questions from the jury members. We have one.
So I still didn't understand which of mechanisms show that the frequency decreases, because the speed of sound increases with the growth of temperature, yes?
Yes.
And the frequency which is due to the bubbles also increases,
Yes.
because the surface tension decreases with the growth
Well,
of temperature.
this is quite messy, so you can't really tell.
How can you explain that the frequency all in all decreases?
That's the coalescence. That's the fact that you have bubbles that are merging, and as the frequency is correlated with 1/r, you get that the radius of the bigger bubble is going to be the radius is going to be bigger, so you get a lower frequency, and so you get a lower sound. And that's this formula. You have 2 bubbles merging of different radius, and this frequency is going to be, because frequency is 1/r, you have a bigger radius, so you have a small frequency.
But where is the temperature here?
Where is the?
Temperature here. Why, with the growth of temperature, this coalescence
Okay, yeah.
appears to be more.
That's been studied in the literature, and it says, because it's quite complicated also, it's the fact that when you have the merging, so there are 2 facts. There are the fact that when you have the 2 bubbles that are going together, it has to eject the air outside, and that depends on the viscosity of the water. So if the temperature increases, the viscosity decreases, so it's going to make the bubble moving easier, because it can eject the fluid more easily. And then when you have, actually the coalescence is something, you have the contact angle time. So this one is linked to the surface tension of the bubble, and this one is going to decrease with the temperature, because the surface tension decreases with the temperature. That's why with the temperature you get a bigger coalescence.
All right. More questions?
So, of course, so now you use the cavity and the change of temperature of the air in the cavity, right? So you
Yes.
measure the air temperature. Yeah.
Yes.
So now suppose, and that's because it's complicated, because the cups can have different shapes and everything. But now suppose I have a completely filled cup with a radius of 1 decimeter. And I have a controlled experiment where I pour liquid from a certain height at a certain rate. Would it then be possible to make it homogeneous?
Yes, with the coalescence. With the coalescence being
Yeah.
easier for this one. But you can't get, with the experiments, we tried the coalescence, and you can't get, it's like 50 size down, but you get not a good prediction, but you can also use a comparative method for this one.
Yeah,
And
so how many points would you need to calibrate?
Actually, what we wanted to do for this one was to take the biggest, the 2. So you have the first frequency that is going to be at 1,000 hertz, and you're going to have the lower one here. And so what we did was to take the amplitude of this one over this amplitude of this one, and you see that with the temperature increasing, you have some kind of a shape like this. So it's quite difficult to have this one is not here, but so it's quite difficult to find a function and to really calibrate it. So I would guess like 5 points to get on the curve, and then you can calibrate it. But otherwise, it's really depending on the experiments we do.
But you could make a thermometer that you had calibrated to a range
Yes, yes. Well, we could get the thermometer, but we also tried, and we get a comparison method that is good for this one, but the predictive method can change really easily because with the Fourier transform, it's quite hard to find the median here. You can have some frequencies that are going to happen here or happen here. It's really a bit messy with the frequencies, so it's not precise enough to do the exact prediction of the temperature.
All right, more questions?
Okay. You in fact measure the temperature of gas in resonator.
Yes.
But I didn't catch. How can you be sure the temperature of water and gas are equal?
Yes. So you have the diffusion process as the water goes into the cavity, and so we said it's about, so in the experiment what we do is we pour the liquid for about 10 seconds, and then we measure, and we found that 10 seconds was the right order of time to get a good precision between our experiments and the theory. So 10 seconds is how we measured that we have transmitted all the heat of we have put the air at the same heat as the water.
We have time for more questions.
So in this tube that you're testing the ion frequencies, so what would be the effects of boiling water, since boiling water is evaporating, and how does these water fumes, how do they affect C? And I mean, did you test this?
That's also interesting because in the setup when we measured the mini-height frequency, we tried with really big bubbles, and so we have the setup over here. We inject the bubbles here, and so if we inject really big bubbles, when they come at the surface, they make a popping sound. But it's quite well. We tried, and we got like all the frequencies that are distributed in the Fourier transform. So it's not that different, because we expect from a shock to have all the frequencies that happen, and then the cavity is going to select some frequencies. I would guess that would be the response, but it was a bit too messy, the exploding bubble, so we're not sure about this.